All right, welcome to topic 2.6. In this topic, we're going to be working on calorimetry, which rolls together the whole concept of what's endothermic and exothermic, along with our specific heat equation. First of all, a calorimeter is a device that's used to do calorimetry, and it's a device that looks at heat flow. This one's just a simple device built with coffee cups, specifically like the styrofoam type, because styrofoam is a really great insulator. What we can use them for is we can put a given amount of mass of water into the cup, get its temperature, and then look at temperature change as a heat or as a heated piece of metal is added to it. We can use that information to identify the composition of an unknown metal. We can, by finding specific heat, we can look at how much heat is transferred between them. The thing, again, with the calorimeter is it allows heat to stay in the system, and we can look at how it's absorbed or released, either during a physical change or a chemical reaction. Okay. In specific heat, we established that Q is representing heat. And so in all lenses, it depends on whose perspective you take. The one thing that's true is that heat can be lost and heat can be gained. And so the heat lost is represented by a negative Q, because again, the negative represents exothermic, as where the positive Q represents endothermic. So something in the system has to lose heat in order for something to gain heat. And again, we can then use look at the amount of heat that was lost or transferred, I should say, by the change in temperature of a quantity of water. Okay, so we're going to go ahead and dive right in. I know the notes have 3 examples. We're only going to work example 1 and 2. Example 3 is particularly rough, and we're going to skip that one. I won't have you guys work that style problem. Okay, so in example 1, it says a 46.2 gram sample of copper is heated to 95.4. It's placed in a calorimeter with 75 grams of water at 19.6 degrees Celsius. The final temperature of both the water and the copper is 21.8 degrees Celsius. What is the specific heat of copper? And the specific heat capacity of water is 4.184. Okay, when we look at this, the copper is starting at a temperature of 95.4. And it ends at a temperature of 21.8. So if we think about the delta T here for the copper, its temperature change is going to be negative. So I'm going to show the setup with this problem in 2 different colors. So what's happening here is because the temperature is dropping for the copper, that means the Q will be negative. And so we're going to make a list of information about the heat related to copper. And then the temperature from water went from 19.6 up to 21.8. So it had a positive change. So that makes the water endothermic, which is why it's positive. And the copper would be exothermic, which is again why the Q is showing as negative. Okay. So then we have MCAT. Because the idea of what we're going to use, and let me rewind here, is that the heat that the copper loses, because it's exothermic, is going to be gained by the water. And we can replace that as MCAT equals the positive MCAT for the water. Okay. So looking at the information here, I know the mass of the copper is 46.2. It asks, what is the specific heat? So the specific heat is my question mark. That's what I'm solving for. So to get delta T, I'm going to take my final temperature, and it ended at 21.8, and I'm going to subtract that from my initial of 95.4. I get a temperature difference of negative 73.6 degrees Celsius. Okay. Now we're going to do the same thing, get our info about the water. And so I have 75 grams of water. The specific heat, and this is a constant, so this will always be the same for water no matter what situation it's in, unless it's in a different state. But we're going to use liquid water, so this isn't going to change. Okay, so then delta T, it ended at 21.8 from 19.6 because delta T is final from initial, and it's 2.2 degrees Celsius. Okay. So now I know that the heat that was lost, and I know it was lost because of the negative temperature change, had to go to the heat in the form of the water because it caused a positive temperature change. Okay, so now I'm going to go ahead and start plugging in my information. So I have negative, and then inside my parentheses, so all I've done here is plugged in my information regarding the heat of the copper. I'm going to do the same thing, but now with water. Okay, so again, all I've done is taken my information and understanding heat was transferred from the copper into the water. And now I need to look and understand how I'm going to break this down mathematically. What we can do is we can multiply what's in the parentheses here. So we get 46.2 times negative 73.6. I'm not going to worry about sig figs till the very end. Oops, put my parenthesis too soon. Neither unit cancels, so I get a gram times a degree Celsius. That's X. And then I'm going to break down the right-hand side by multiplying. So I'm going to take 75 times 4.184 times 2.2. Let's talk units here. When I multiplied, grams canceled and the degrees Celsius canceled. So the right-hand side, I'm left with joules. Okay, so all I did was condense my information by using algebraic processes. Okay, now the left-hand side, if I know my directions here, this negative distributes in. So all that does to change the left-hand side is this becomes a positive 3,400.32 grams times degrees Celsius X equal to 690.36 joules. Okay, I need to get X on its own, and I do that through division. Okay, so X I will get through dividing. So 690.36 divided by 3,400.32. And I get this long number. This is where I need to look at sig figs. Again, that comes from our givens. The temperature only has 2 sig figs, so I'm going to keep 2. The 0 in the front is not significant, so 0.20 because nothing rounds. Lastly, nothing is canceling here, which makes sense because we're finding specific heat. So joules per gram degree Celsius, and we have found our specific heat for the copper metal, right? Example 2 is kind of the same idea. Oh, I'm going the wrong direction. There we go. And it's talking about iron being heated up, because that's the trend here, is that a metal that is heated is added to water of a lower temperature so we can study some property of the metal. So we have a 500 gram piece of copper is heated in a flame and it's dropped into water at 10 degrees Celsius. The temperature of the water rises to 90. Okay. Well, I see here that the water started at 10 and it ended at 90. So that tells me that, like the prior example, the iron is what's exothermic and the water is what's endothermic because temperature is increasing. And that's how I know which one's going to be my negative and which is going to be my positive, because exothermic is negative. It's a release of heat. Endothermic is positive because it's absorbing heat. And we see a positive temperature change. Okay, so the mass of the iron is 500 grams. The specific heat is given to us. It's the very last statement of 0.473. And the delta T, and I didn't mention this from the prior problem, the final temperature in these systems are the same. The final temperature of the water is the exact same final temperature of the metal because they are going to come to what's a point of thermal equilibrium where they're at the same temperature because heat is not flowing between them at this point. Okay, so if the final temperature of the water was 90, that's also the final temperature of the metal. Okay, it asks how hot, so I know that it has something to do with its temperature, and it wants to know how hot was the metal when it was removed from the flame. So delta T is my question mark because our temperature final is 90 degrees. But I do not know my temperature initial. Okay, so this is kind of a twofold problem here. So I'm going to slide this over a little bit. And we should be able to get our information then for the water. So we have 400 grams. Water, it doesn't tell us a specific heat, but I mentioned in the last problem this is a constant. So it's the 4.184 joules per gram degree Celsius. Okay. The water temperature rose to 90. It started at 10. So I take 90 minus 10 to get 80.0 for our temperature change. Okay. So Q of the metal is equaling the Q of the water. Okay. And we have negative MCAT is equal to the positive MCAT of the water. So we have 500 grams of the iron times the specific heat of 0.473 and X for delta T right now. I'm going to go ahead and plug in my information from the water side. Okay. There is more than one way to get to the answer. How you want to break it down algebraically is up to you. I'm going to simplify the parentheses first. So I get negative parenthesis 236.5. And my grams have canceled here through multiplying. So I get joule per degree Celsius X equals, and then I'm going to go ahead and simplify this out by taking 400 times 4.184 times 80. We can keep 3 sig, or I'm going to rewind that. Don't worry about sig figs at this point because we're not at our final answer. Okay. Looking at unit analysis here, grams have canceled, degrees Celsius have canceled. We have joules. Okay. This negative distributes in, so this is different in that our X is going to be negative here. 236.5 joules degrees Celsius X. And this does nothing to the right-hand side. So all I did was distribute in my negative. Okay, how do we get X on its own? By dividing. Specifically by the negative 236.5 joules per degree Celsius, where X represents the delta T. Now let's talk sig figs. Again, the givens decide that. 500 has 4, 0.437 has 3, 400 has 4, water specific heat has 4, and then the temperature is 3. So we can keep 3. Okay. So when I divide this by negative 236.5, I get to a whole number because that'll give me 3 sig figs, negative 566 degrees Celsius, because joules has now canceled. That makes sense. Degree Celsius is a unit for temperature. We're not done. because that would be too easy. Okay, think about this. Our temperature should be negative because the iron was exothermic, so it lost heat. So our temperature is going to be, again, negative. So we have to go back to find delta T with TF minus TI, and I'm going to plug this in. We know it ended at 90. Okay. We get this on its own. We're going to take negative 566 minus 90 for negative 656. But that's equal to a negative x. We need to make it positive, so we just flip the sign. And so the initial temperature of the metal in the flame was 656 degrees. It was cooled to 90, and that's where we got a temperature difference of negative 566. So that is how you work through calorimetry. And again, we're not doing the style of problems in example 3. Let me know if you have questions or concerns.